In this video, we're going to use our vector knowledge that we've learned so far to solve a real-life problem. In fact, the problem is going to be about an airplane flying along. There's some wind behind it. We've got its airspeed and we've got to work out its ground speed. And we're just going to use dot products and we're going to use some vectors to represent this problem and solve it. Right, so here's the problem. An airplane is flying on a bearing of 120 degrees. So we start off looking north, as we have here, come around in a clockwise direction of 120 degrees. This is the direction that our plane is flying in. It has an airspeed of 300 miles per hour. Now that means that it's travelling at 300 miles per hour in relation to the air around it. Now the next sentence says that there's a 30 mile an hour wind blowing from the north directly southwards. So we've got a 30 mile an hour wind blowing in this direction. So if it's travelling 300 mile per hour in relation to the wind relative to the air around it, that air is travelling southwards at 30 miles an hour to start off with. So that's kind of an additional component of velocity blowing in the southward direction, travelling in that southward direction. Now we've got to find the actual bearing of the plane and its ground speed. So we're going to represent all this information in a vector diagram, and then we're going to use some of our vector knowledge that we've gained in order to solve that problem. Right, so here's our diagram. We've got vector A represents the airspeed or the air velocity of the aircraft. So it's on a bearing of 120 degrees, as we said before, and the magnitude of vector A is going to be 300 because that's the speed with which it's travelling. So the magnitude of vector A is 300, moving in that direction. Now because the wind is travelling at 30 miles an hour in this direction, the ground speed is going to have this extra component of southerly speed to it. So the ground speed is going to be slightly bigger than that, and it's going to be heading in a slightly more southerly direction. And we're also trying to find the size of this angle here, call that theta, and if we add that theta to the 120 degrees we had up here, that will give us the bearing of the ground speed, the actual bearing that the aircraft's heading on. Now what you might see is we've got two vectors and we're trying to find the angle between them, so we're going to be using vector dot products in here, and we're also going to be looking at magnitudes of vectors, so we're going to be using some of those skills as well. So let's try and fill in some of the details about vector A. Well, it's got an x component, which is, in this case, it's an easterly direction on our diagram, and it's got a y component, which in this case is in the southerly direction, so it's going to be a negative number. It's heading downwards in the negative y direction. We said that the magnitude of that vector was 300 because it's travelling at 300 miles per hour. So let's just do a little bit of work on this triangle that we've created to work out what the x component and the y component are. So I've just drawn in my west, east and south, and I've filled in this angle here of 30 degrees because the angle between the north and the east direction is 90 degrees, which leaves 30 degrees for this angle here. So just looking at the cosine of that then, we've got a right angle triangle. The cosine of 30 degrees is the adjacent side over the hypotenuse, so that's AX over 300. So we can rearrange that to work out what AX is simply by multiplying both sides by 300. So that's AX is 300 cos 30, and then cos 30 of course is root 3 over 2. So when we work all that out, the easterly component of A's velocity is 150 root 3 miles per hour. Okay, let's look at a y now, the y component. And sine of 30 is the opposite side over the hypotenuse, which is AY over 300, which again multiply both sides by 300 and we get 300 sine 30. Now sine 30 is a half, so that equals 150. So the airplane's speed, if you like, in the easterly direction is 150 root 3, and in the southerly direction is 150 miles per hour. So we've worked out what the components of the A vector are. Now the one thing that we do have to watch out for is that, remember, the positive y direction would be going in a more northerly direction, but because we're heading towards the south, we've got a negative y component. So that 150 miles per hour is in the southerly direction. So on our scale, the a vector is going to be this here, 150 root 3 negative 150. So moving on to the ground speed vector, we can see that the horizontal component is exactly the same as the airspeed. The extra wind was only blowing in the southerly direction, so it's not affecting that horizontal component. So the horizontal component, the x component of the ground speed, is the same as for the airspeed. Now with the southerly component, the y component, we've got this extra 30 miles an hour kicking in. So we've got whatever the airspeed was up here, but we're adding an extra 30 miles an hour to that. So the ground speed y component is going to be 150, same as airspeed, plus the extra 30 is 180 miles per hour. And again, because that is in a southerly direction, not a northerly direction, it's the negative y component, so it's going to be minus 180 miles an hour. So our g vector is 150 root 3 for the x component, same as the airspeed, and negative 180, that extra 30 miles an hour in the y component. So we've worked out our velocity vectors then for the airspeed and the ground speed, a and g vectors, and what we now need to do is work out what the magnitude of that ground speed is. So we're going to try and find the magnitude of g. And to do that, remember, we square the x component and we add that to the square of the y component. Calculating those, we get the square root of 99,900, which is equal to 30 root 111, if we want to be exact about it, or to one decimal place, 316.1 miles per hour. So the magnitude of the ground speed is 316.1 miles per hour to one decimal place. So that's our ground speed then. Now what we need to do is work out the size of this angle here so that we can add it to 120 degrees and get the size of our bearing. And to work out the angle, we're going to use the dot product of the unit vectors in the direction of the airspeed and the ground speed. So a over the magnitude of a dot g over the magnitude of g in this case. So the magnitude of a is the components squared and added together, and take the square root of that. We've already worked out the magnitude of g, so we can now just simplify that down. And to work out these dot products, I'm going to take this component and multiply by that component and add it to this component multiplied by this component. So that's what that gives us. Remember, because we're doing dot products, we mustn't use the cross multiplication sign. We need to be consistent and use those dots for multiplying the numbers together. So just got the common denominator there already. Multiplying those numbers out, adding them together, gives us 21 over 2 root 111. So what we're saying is that this cos theta here is equal to 21 over 2 root 111. So if I do cos to the minus 1 of this, it will tell me what theta is. And to one decimal place, that gives us 4.7 degrees. Now, it's just worth mentioning at this point, I haven't been rounding these numbers as I've been going along. I've been trying to keep them in surd format, root format, just to keep the accuracy in the question as long as possible. So it's not always possible to do that because some numbers don't come out quite as easily, or your calculator can't handle them in that format, but if they can, it's best to work in that format for as long as possible. Now remember in our question, so we've just worked out this bit here, so we've got to add that to 120 to work out what the actual bearing was. So that's going to give us an answer of 124.7 degrees. So there we have it. Our answers were 316.1 miles per hour to one decimal place for the ground speed and 124.7 degrees to one decimal place for the bearing. So let's just kind of recap some top tips as we go. Always worth doing a diagram. So that definitely helped us doing a diagram. We represented the airspeed and the ground speed as vectors, so that turned out to be quite useful. We were able to work out the magnitude of vector g fairly easily, just using effectively the Pythagorean theorem. We were trying to keep our values in surd format, in this root format, as far as possible, to keep the numbers as accurate as possible as well. And we were also able to use the cos theta equals the dot product of the unit vector in each direction to work out the angle between those two vectors. So hopefully that's given you a bit more insight into using vectors to solve some problems.